Let's say you want to go to space. Well, space is commonly defined at the Kármán line, conventionally set at 100 kilometers above the surface of the Earth, and to reach it, you'll have to get creative. In fact, you can't simply use a traditional aircraft to reach such heights. These kind of planes work by interacting with the atmosphere. Their wings are designed to generate lift through a pressure gradient given by their curvature, but this can only happen if there is airflow around the wing. At our altitude of 100 kilometers, we can empirically verify that the air density is extremely low, as shown in these graphs. This is because Earth's gravity keeps most of the atmosphere near the surface. The wings of our aircraft won't have any atmosphere to interact with, and we will never reach space. Furthermore, the engines won't have any air to use to generate thrust. We must find a different solution, something that allows us to generate a force even when there is nothing but a vacuum. Here is where Newton's third law of motion comes into play. This principle of motion states that for a force applied to an object A on object B exerts back an equal force and magnitude, but opposite in direction. This law is often abbreviated to, for every action there is an equal but opposite reaction. This means that when we push against something, that something pushes against us as well. If we consider force to be the rate of change of momentum, we can see that this principle implies an important fact of our universe: conservation of momentum. Let's see an example. If we were on a skateboard and then decided to throw a heavy object, we would move backwards. This is because we must contrast the momentum of the heavy mass by moving in the opposite direction. Our velocity is expressed by this formula. We can use this principle to help us reach space. All we have to do is throw a large amount of mass in the opposite direction in which we want to go. Since we can't have astronauts manually throwing bags of sand off the craft as if it were a hot air balloon, a common method used by rocket scientists is to accelerate mass by generating a pressure gradient, taking advantage of the same physical principle that allows planes to fly. Before we can proceed, we must outline the concept of pressure. Pressure is defined as the amount of force exerted per area. We often encounter pressure in our everyday life. When we push against a small object, like a needle or a pen, this exerts, for Newton's third law, a very high pressure on our hand because the surface that pushes back on us is very small. Conversely, if we push against a large object, like a table, with the same force, we feel no pain at all. When talking about static gases and pressure, we intend the force exerted by the many molecules that make up the gas against the walls of its container. There is nothing special about this wall. We could measure the pressure against the surface inside the gas, oriented in any way, and still obtain the same value of pressure. If we instead consider moving gases and apply the principle of conservation of energy between 2 points in a fluid, we get this equation, commonly known as Bernoulli's equation. A consequence of which is a tendency of fluids, such as gases or liquids, to move from a high pressure area to a low pressure area. In fact, if the pressure decreases, the velocity must increase. To better understand how pressure can be used to generate thrust, let's consider a balloon. When inflated, the air inside the balloon has a greater pressure than the air outside. This means there is a pressure gradient that keeps the balloon stretched. If we open the balloon, the air will flow outside, pushing our balloon in the opposite direction. Effectively, we're throwing air outside of the balloon. We must introduce a new concept: mass flow rate. This term indicates simply the amount of mass which passes per unit of time. If we have a mass of 1 kilogram moving for 1 second, we then have a mass flow rate of 1 kilogram a second. It's often used to describe the amount of mass displaced in a moving fluid. By using the density of the fluid, its velocity, and the area that it passes through, we can rewrite the mass flow rate. Thinking of air as a fluid with mass explains how its movement can generate thrust, similarly to how throwing an object would. There is an important relationship between pressure difference and mass flow rate. The greater the pressure difference between 2 points, the greater the mass flow rate. A rocket works similarly to a balloon. Inside the spacecraft, a high-pressure gas must be created. and then expelled to create thrust. And here lays an important distinction between rocket engines and air-breathing engines used on aircrafts. The latter use the air around them to generate high-pressure gases, while the former must carry to space both the fuel and the oxidizer. But how do we create and expel high-pressure gas? One option is chemical propulsion, in which fuel and oxidizer react to generate propellant. Chemical propulsion can be of different kinds: liquid, solid, or hybrid. As the name suggests, in liquid propulsion systems, the fuel and oxidizer are in liquid phase and are then mixed and ignited. These liquids often have to stay at very low temperature. Maintaining the tanks at high pressure and controlling the fuel pumps requires complicated engineering solutions, but on the other hand, it makes it possible to control the thrust by opening and closing the valves. In solid propulsion systems, the fuel and oxidizer are cast in a solid material that only requires ignition to burn. Once ignited, it's hard to control how the propellant burns and can't be turned off, but it's easy to maintain and handle. Hybrid systems use both a solid fuel grain and a liquid oxidizer, allowing for greater control and higher thrust, combining the best aspects of the other two systems. Another option is nuclear propulsion, in which the heat generated by a fission nuclear reactor converts liquid hydrogen in high-temperature gas without necessitating combustion. Various prototypes have been built, but none have flown to today. Going back to the principle of conservation of momentum, there are even other solutions that don't involve gases, but rather ions accelerated by magnetic fields. This kind of propulsion provides a very low thrust, but allows for long and continuous use, apt for changing orbit once in space.